the main question we ask is whether the current explanations can actually predict generalization in different neural nets. Sorry, just let me not forget this. Most of the experiments are done by Yiding, who's a resident at resident at Google, and this joint work with Yiding, Hossein, Dilip, and Sami. Yeah, so we train neural nets for different applications, and we always see successes. But what happens behind the scene is that we choose different hyperparameters like width, depth, batch size, activation, regularization, and some of these hyperparameters work, some of them don't work. We have no idea what kind of choice would give us good result and what choices are not good. And basically, like right now, we have no clue what kind of networks generalize. So we basically want to understand these different choices that end up learning different networks, what type of networks would generalize or not. So here you see like one example of training such a network. To be more specific, we always given a training set of examples, and we train a network to find a hypothesis F that predicts labels correctly at the training set. But what we really care about is to measure the performance on some set of unseen examples. So we call that test error. So test error can be written as training error on the set we have, plus the gap between training and test, which we call generalization gap. And here I show it with G of F. This is the main quantity that we care about. Because training error, like if it was just minimizing training error, we could just memorize everything. This is what generalization gap is, what makes it really difficult. And we want to understand in what kind of networks generalize better. So how do we predict the generalization gap of a hypothesis? What's the best way to predict if a hypothesis is going to generalize or not? So to make it a little bit more formal, I'm interested in some measure that's going to act like a predictor of generalization. Basically, I want my measure to be such that given any two networks, if the measure is lower on the first network, then the generalization must be better on the first network. So the order should be preserved under this measure. In that sense, I can always sort any set of networks based on this measure, and it gives me the right order in terms of their generalization. And of course, I don't want this measure to have access to data distribution. Otherwise, you can cheat and just like get an estimate that how it's going to work, and it's not going to be really informative about the generalization.
Excuse me. When you say measure, is it a function or like a measure in the sense of real analysis?
It's a function from space of networks to just a real number that you can use it to sort. Yeah, thank you. So how can we come up with these kind of measures? Is there a guiding principle that tell us like where to start, how to come up with these different hypotheses of generalization? And of course, people have mentioned this several times here. Occam's razor can be used as a guiding principle, which says simplest hypothesis is most likely the right one. So we should be looking at some sort of complexity measure, something that tells us how complex is the function we are learning. So our measure, again, is going to be lower when our network is simpler in some sense and higher if it's more complex. And of course, then the question is, what's the right notion of complexity? Do we want to just count number of parameters? Do we have some smarter way of understanding the complexity of the network? And that's the question we are asking here. This is arguably the most fundamental question in learning. What makes a system learn from data? And we are not interested in just bounding the generalization error, because that you can do with a validation set. What we are really interested in is an understanding of what properties allows these networks to generalize. And if you have such an understanding, you can design optimization algorithms using these properties, or add regularizers, or even design architectures that have these properties in themselves to end up with better generalization. Unfortunately, even though this is a fundamental question, this is pretty much an open research direction, and there are only scattered theories floating around based on empirical work or theoretical work, and we don't know much about it. One approach to understanding generalization is generalization balance, basically proving that the generalization gap, which we're interested in, is bounded by something else. And usually it looks like square root of this complexity measure divided by number of examples. For example, this can be roughly number of parameters if you use VC dimension. The main issue with just looking at generalization bound is that, first of all, it's hard to prove generalization bounds for every new architecture that we see tomorrow and the next day. Like, we can try really hard to prove something about fully connected networks, but then what do we do about transformer? Can we say something about transformer? That would be hard. And the other issue is that these bounds are not tight, so it's not necessarily the case that a tighter bound is a better bound. For example, if you look at this plot, let's say x-axis are different models, and y-axis is the generalization. So if I sort models based on their generalization, this red curve would correspond to the generalization error. And then I can have two generalization bounds. The blue one is tighter than the green one, but the green one is more indicative of what type of model would generalize better, right? So if I want to choose between these two generalization bounds, the green and blue, I would prefer green because green is more indicative of what kind of models generalize better. And of course, you can ask Dan Roy about this, that like all these bounds are vacuous, so they are greater than 1. So anyway, you cannot really rely on the theorem to actually prove that this measure is telling you something interesting. The other way that people have looked at this has been looking at correlation when you change a hyperparameter. For example, here, my pointer is not okay. Okay. That's going to be tough without the pointer. Oh, came back. So here, the plot on the left shows the training and test error. The x-axis is width of the network. And as you can see, when you make the network wider, the test error becomes better and better while the training error is 0. So the generalization gap becomes lower. And then on the right plot, we are comparing different measures. And you can see all of them except one increase with width and one of them decreases. And then, like typically, we declare success here because we say there's correlation between this measure and the generalization error. But there are several fundamental problems with this. One is that we only change one hyperparameter, right? So it's very sensitive. So I could potentially come up with a measure that is 1 over width, and that would correlate with generalization. But does that tell me anything about generalization really? No, because I just like incorporated what I really wanted in the measure. And in most of these methods, people actually look at data and then come up with a hypothesis on the data that they already looked at. So that's a problematic approach. So in this work, we try to come up with experimental design where we go slightly beyond correlation and we ran larger scale empirical, larger scale experiments on neural networks, and we looked at over 40 different measures that are like suggested in different papers or a combination of them, and we tried to see which one can actually tell us something interesting about generalization. And I'm going to show you some of the surprising observations we have. So let me just give you high-level design of the experiment. We looked at VGG architectures on CFAR dataset, and what we did is that we changed 7 different hyperparameters, which are width, depth, learning rate, batch size, weight decay, dropout, and optimization method. And for each of them, we had 3 different choices. So that gives us 3 to the 7 different models, like 2,000 models roughly. And we chose these hyperparameters such that all these models train properly, and they converge to, almost all of them converge to cross entropy 0.01. And then we just compare different complexity measures to see which one would actually predict generalization better. Okay, so the first thing we looked at was just overall rank correlation, basically how well these measures can rank models based on their generalization. So G, again, is the generalization gap, which is gap between training and test error. And mu is our complexity measure that we want to evaluate. And what we do is that we just look at all possible pairs and sine of G of F1 minus F2 times sine of U of F1 minus U of F2. So if this is positive, it means that the complexity measure gets the order right. If it's -1, it gets the order wrong. So the overall number is going to be between -1 and 1, and it tells us how good this complexity measure correlates with generalization. Well, we can also go slightly beyond checking overall correlation. We can run control experiments. We can fix all hyperparameters except one, and then see if this measure can predict generalization if we only change one of these hyperparameters. So that would be our second experiment. So for each hyperparameter, we fix everything else, and we only change that hyperparameter, and then we check rank correlation. And we can also look at the expected performance we get on different hyperparameters. And we were trying to figure this out, and it was around that time that I was chatting with Brady, who's a PhD student at Mila, and he asked this question that is correlation really enough when you're looking at these things, or you should think deeper? And that made us think more about like what we're doing and what is the real thing we're looking at. If you're looking, we're interested in finding out if this measure is a cause of generalization, we should probably go slightly beyond correlation. To make it more formal, you could observe correlation in two scenarios. One scenario is that the change of hyperparameter would change the complexity measure, and change of hyperparameter would affect the generalization. But the complexity measure itself has no relationship with generalization. Basically, there is no causal relationship between these two. The second potential scenario is that the change of hyperparameter changes complexity measure, and that is the reason you get a different generalization. So we want to basically see which one is true. We don't want to only look at correlation because it could be artificial relationship between the complexity measure and generalization. In order to figure out which one is true, what you can do is that you can check the mutual information between your complexity measure and generalization conditioned on a hyperparameter. So if there is a direct relationship between them, when you condition on a hyperparameter, the mutual information is going to be high. If there is no direct relationship and you condition on hyperparameter, mutual information is going to be 0. Basically, they're going to be independent. So that's what we also look at. So let me just start by showing you some results. This is just some baselines. I'm going to first explain what this table means. So here, the table above is just looking at different correlation measures, and the one below is mutual information. Each column here is, so for this column, for example, is when I fix all hyperparameters except batch size, and I change batch size, and then I just measure how correlated is this measure here to generalization. So here, I only change batch size, everything else is fixed. Here, I only change dropout, and then this is overall correlation, which is basically, I just look at all possible pairs and look at correlation. This column is expected value of these controlled experiments columns. So just sum of these expected average of these values is going to be here. And this is overall correlation. This is, of course, harder because I'm only changing one hyperparameter, and this is controlled experiment, so these numbers are generally lower. The second table is experiments related to independence and mutual information. Each column here is basically mutual information between the measure and generalization conditioned on this hyperparameter. So this says if I know the batch size of these two different models, then how good I can predict generalization. And this number is between 0 and 1. So 1 means if I know the batch size, I can predict the generalization perfectly. And then you can see different numbers for conditioning on different hyperparameters. This is overall mutual information if you don't condition on anything. And this roughly corresponds to correlation. There is actually one-to-one mapping between overall mutual information of the measure and generalization and the correlation. But then this is the hard part, which is when you condition on hyperparameters, what's the best mutual information you can get? And in general, this is going to be much lower. So these are the baselines. So if you knew the test error, of course you're going to just perfectly predict the order, right? So this number is going to be 1. But then we also asked, just to see how hard is the task, we said, what if you have access to the test error plus minus 0.02? Then you get something like this number. So this roughly tells you how difficult is this task. If you get these numbers, you're roughly as good as having access to test error plus minus 0.02. And then this is another simpler task. And you can see that these correlation numbers are too high, but when you condition, you generally get low mutual information. So numerically, these numbers are like lower in general. Okay, so one thing, for example, to see here is that if you fix all other hyperparameters except depth, you're going to get higher numbers in terms of correlation compared to fixing optimizer, which says predicting generalization if you only change the optimizer is harder than predicting generalization when you change depth. So some of these tasks, some of these controlled experiments are in general harder than the other ones to predict. So the first thing we look at is just to get a sense of how important are these hyperparameters. We look at like how good we could predict generalization if we know the hyperparameter. So if I know the batch size, if two models have every hyperparameter is the same for two models except the batch size, could I predict generalization or not? So for example, for batch size, there's this hypothesis that people talk about, which is a smaller batch size generalize better. So let's see if that's the case. For dropout, we usually believe that more dropout is better. For learning rate, we believe larger learning rate is better. Depth, we believe deeper networks are better. We usually think SGD generalizes better than Adam and that better than RMS prop, and more weight decay is usually better, wider network is better. So we're gonna test first to see how predictive are these hypotheses, just to get a sense of how difficult is each of these tasks. If you knew the hyperparameter, and also like just to get a sense of how informative are these numbers, we also report random guess. So in terms of canonical ordering, which is like basically if you know the batch size or other hyperparameter, how well you could predict, you can see that this is indeed the case that smaller batch size generalizes better, and you can pretty easily predict generalization using batch size. More dropout is better, higher learning rate is better, deeper networks are better, but it was not the case for optimizers. So it was not clear that, like, at least in our experiment, SGD was not better than Adam or RMS prop. And also, wider networks did not generalize better necessarily. So we have, so these two are the cases where the canonical ordering cannot predict generalization. Also, like, just to get a sense of how informative are these numbers, if you had random guess, these are the typical numbers you would get. Okay, so the first set of measures we look at is VC dimension and number of parameters. Of course, you don't expect VC dimension to predict the batch size, predict generalization in case of changing batch size, because it's going to be the same. So the only ones that are potentially predictive are changing width and depth, and you can see that everywhere else it's going to be 0 because it's not going to change. For depth and width, it has negative correlation, which makes sense because overparameterization helps with generalization, but VC dimension and number of parameters are telling us the opposite of the story. So overall, we are going to have negative correlation. But when we condition on hyperparameters, we actually get 0 conditional mutual information. Because if I know the depth and width of the network, I can perfectly predict VC dimension. So if I condition on them, there's no mutual information between VC dimension or number of parameters and generalization. So now we go to norm-based measures. There's this bound by Bartlett and others, and it's been extended to convolutional network, which basically says the generalization corresponds to lots of terms, and the main term here is just product of a spectral norm of the layers, but there are like a whole bunch of other terms, but you can think of it as just product of a spectral norm of the layers. So this is a generalization bound that suggests, like, if the product of a spectral norm of the layers is large, you're going to generalize worse. So we look at the whole generalization bound and also the simplified version, which is just looking at product of a spectral norm divided by margin. You don't need to look at the equation if you're not familiar with the generalization bound here. So you can just think about it as product of a spectral norm of the layers. And now we want to see how well it's going to generalize. So we were surprised to see that there is actually a strong negative correlation. So we expected, like worst case, we expected that not to correlate, but we actually observe a strong negative correlation. And this correlation is, I would say, it's real because it's not just overall negatively correlated, but no matter what hyperparameter you fix and what you change, it's negatively correlated with generalization. So if I only change batch size, it's negatively correlated. If I only change dropout, it's negatively correlated. So it says something about complexity, and it's probably something that we don't understand because that shouldn't be the case, that models with larger spectral norms don't generalize.
How do we compute the spectrum?
It's given in a paper by Sergey et al., which is like the true spectral norm of the convolution parameters. It's not just like flattening and calculating spectral norm.
No, I mean to do a specialization in the experiment?
This is, no, you don't add it. It's just like you run SGD and then you measure a spectral norm at the end. So you just look at the spectral norm of the trained network.
But if you have batch norms, then the spectral norm.
Oh, about the batch norm. So what we do is that whenever we always train with the batch norm, and then we reparameterize the network to the equivalent one that represents the same function, but without the batch norm. And then we measure a spectral norm.
But there are some scaling on inputs, right?
The scaling does not change.
So you need to do the scaling on the inputs.
scale of the input is the same in all experiments because it's the same data set. So yeah, so that's very surprising. We see negative correlation here, and this is something we don't understand. Next, we look at other hypotheses that people have been talking about. One is distance. There's been a lot of papers showing that distance to initialization might correlate with generalization. There are lots of evidence. The other one is L2 norm of parameters, weight decay, which we all use when training neural networks. And the last thing we look at is just the same weight decay, except like you first normalize the network so that all layers have the same Frobenius norm, and then you calculate the sum of Frobenius norm of the layers. So this is like a more normalized version of the weight decay. So let's first look at the distance to initialization. This is again negatively correlated. So it says the ones that actually have larger distance to initialization, in general, they would generalize better. It's not as a strong negative correlation as a spectral bond, but I would say this is still interesting that why we see negative correlation. And again, the negative correlation is almost everywhere except the case of depth. So there's something interesting going on here. We were hoping that L2 norm at least correlates because we use it in practice. And that was uncorrelated. So even L2 norm doesn't explain anything. But when we balanced the network, we got some high correlation. Oops, sorry. We got some high correlation. Unfortunately, when we did this more principled way of looking at the numbers, which is conditional mutual information, then the number dropped significantly. So the mutual information was 0.13, and when we do condition on set of hyperparameters, a set of size 2 hyperparameters, it suddenly reduces to 0.01. So even balanced L2 norm does not explain. But then we said, okay, maybe the fact that balanced L2 norm is at least positively correlated and spectral norm is negatively correlated, maybe the ratio of them is the answer. Maybe we really want to look at ratio of Frobenius to spectral norm, which roughly corresponds to a distribution of eigenvalues in the network. So that's the next thing we look at. And then we also look at the path norm, which is basically squaring calculating the square of all hyperparameters, and then on that network feeding in an all one vector and then doing a forward pass. So that corresponds to path norm. So unfortunately, ratio of Frobenius to spectral norm was not correlated. So our hypothesis was not correct. But the path norm had some positive correlation. It was, in fact, positively correlated with everything except dropout. And overall, it was better than other norm-based bounds, even though, in general, all of them were disappointing. So we just learned that norm-based bounds, it seems in general, they are not really good. They're not really powerful in terms of capturing generalization. And one other interesting observation was that, in general, they're really weak in capturing why networks with dropout generalize better. And then we also looked at the flatness-based measures. So these measures basically ask the question of how flat is the solution. One way is more like pack-based bounds, where you add Gaussian perturbation to the final solution, and you measure the flatness of the solution. And then what you do is that you just measure the ratio of the norm of the parameters to the perturbation, the variance of the perturbation you add. So that corresponds roughly to pack-based bounds. And then we also look at the other version, which is worst-case perturbation. That was suggested by Keskar et al. So instead of Gaussian noise, we add worst-case noise perturbation here and basically measure the same thing. And now we saw some slightly better numbers. So both of them have overall positive correlation, and worst case sharpness, worst case perturbation was slightly better in overall correlation, but after looking at conditional mutual information, they were roughly the same. But then we realized that the norms are not really informative. What if we do something that seems like a little bit crazy, which is like remove the norm? Just look at the perturbation. And this is the reason we thought of this was one reason was that the norms were not informative. The other one was that the original work by Keskar and others were also not really dividing by the norm here. So we looked at that, and then we realized that if you do that, the pack-based one gives us much better conditional mutual information. So we said, okay, maybe Keskar et al. Was doing already something interesting. So let's go all the way and do something more crazy, which is similar to what they tried. And that says like you perturb each parameter with respect to its magnitude. So if a parameter has large magnitude, you perturb it more. If it has smaller magnitude, you perturb it less. What that means is that you never switch the sign of a parameter. If it's plus 7, you only perturb it by some magnitude that's less than 7, so the sign never flips. And now again, check this number. Now we are so far from having any reasonable generalization bound because this is not anything close to a generalization bound. And now we saw something really interesting. In case of worst case sharpness, we got a very good conditional mutual information, and we have positive correlation with all hyperparameters. In fact, we are almost as good as, so sharpness, which is just one number, is almost as good as knowing the hyperparameter that you're changing. So each of these hyperparameters are very powerful if you only change them, but not predictive if you change something else. But sharpness is almost equally powerful, except for a case of dropout. It was equally powerful as knowing the hyperparameter you're changing. And even for dropout, this is the only one that positively correlates with changing with generalization if you change dropout.
Can you say, is this last thing related to the largest eigenvalue of the Hessian? Is it the same?
I doubt so because it's, I mean, maybe, but I don't think so because it's, Hessian is just like a local information. So this is more like the amount of change in the loss is so high that we actually need to do search in a larger space. So local information does not capture that, does not capture the overall sharpness. You need some smoothness probably before looking at like something like Hessian. Yeah.
So I don't know why, so like none of the generalization bound says that there's a correlation, right? So nobody promised that the generalization bound correlates with the,
yes.
the real test error. So it's only a bound.
Yes.
Right? So I think I would only, a priori I would only expect correlation when you minimize the bound. Because now you reach the extreme point that the bound kind of like is close to the real generalization error. So I don't know why this is surprising in some sense.
Well, when you minimize the bound, you still cannot even expect correlation because it could be the case that the optimization algorithm would just like adding the regularizer would just ruin the optimization algorithm. But the question is, in the first place, why do we actually have generalization bounds if it's not for getting the predictive power? Because we can always check validation set, right? I'm not saying, okay, so what I'm saying is that the only reason I could find the bounds useful is to generate a hypothesis that can tell us what kind of networks generalize better.
I think the bound is useful because when you minimize the bound, you are not going to overfit. At least it's a meaningful regularizer. So that's why the bound is false. So I know that if I minimize this complex measure, then at least I have some guarantee that I'm not going to overfit.
Yes.
That's why I think the correlation bound test probably should be done on those cases where you minimize the bound.
That's the main problem with checking correlation when you minimize the bound is that since there is implicit regularization in the optimization algorithm, so if I add, let's say I do dropout, right? Dropout is not a bound. But when you add it, because it's orthogonal to some implicit regularization that's going on, it's going to improve, right? But that doesn't mean that dropout is the right bound. It's not even a bound. So if your bound is somehow doing almost the same thing as implicit regularization, adding it is not going to change anything. And also the other issue is that when you add the bound, it changes the optimization surface. Ideally, if I had the black box method, that I could do the following experiments: minimize, find a solution with zero loss with minimum generalization bound, right?
Yeah, so
if I had that, then that was the best experiment.
Yeah, maybe you can take this offline, but I mean, I know that there is issues when you minimize the bound as well, but that doesn't justify we should do this, right? So, like.
Yeah, so we can argue which one is, yeah. It's not. I definitely don't think this is the final answer. So this is just like, we have to figure out a setting where everyone agrees that this is the right way to compare different complexity measures. But the ones that are predictive, that says something, because so it's, what it says is that, so one thing you can say is that this roughly captures the implicit regularization. You're implicitly regularizing something, right? And you observe that sharpness, for example, predicts generalization in that case. So what it says is that sharpness is probably telling you what implicit regularization is doing, not that exact bound. And lastly, we also looked at a couple of measures that relate to optimization. There are two views here. One paper says faster training gives you better generalization. Another paper says faster training, which is like in case of like smarter optimization algorithms, gives you worse generalization. So we asked this question, and we looked at basically number of steps you need to get to cross entropy 0.1, and number of steps you need to get from 0.1 to 0.01. And then we want to see if there's correlation. There is actually negative correlation in case of number of steps to 0.1, which is interesting, and that says faster optimization means worse generalization in this case. And the other one was not correlated. So early in the optimization, the speed of optimization is indicative of generalization. The other thing we look at is gradient noise, which people usually use to argue about the the learning rate. So here we check gradient noise as first epoch and at the final model. And what we observe is that at the first epoch, it's not correlated, but actually gradient noise at the final model is very indicative of generalization. It's actually positively correlated with all the different hyperparameter changes, which is really interesting. I don't know of a generalization bound that depends on this, but this could be subject of future work. So overall, I can say that there are 4 measures that are indicative of generalization. One was product of a spectral norm, which of course had the opposite direction, but still very informative. We have to figure out why. The other measures are sharpness that's based on the magnitude, packed Bayesian bound, and gradient noise. All of these measures are consistently positively or negatively correlated with different hyperparameters, except packed Bayes, which didn't capture dropout. But all of them are, the rest of them are basically consistently correlated. And one other thing is that, again, to look at the difference between conditioning and not conditioning, spectral bound had high mutual information, but when we conditioned, it was much lower. But the amount of drop in the sharpness was much less than spectral bound. Anyways, so we looked at different, like 2,000 networks, and we tried to evaluate different complexity measures. What we learned from this was that norm-based measures were not really capturing generalization, and flatness-based measures were more promising. Also, I think optimization-based measures can have great potential for future work. This is just beginning of trying to figure out what's the right way to evaluate. And as you saw this discussion, I think there should be some high-level discussion in the community that how do we want to decide if something is explaining generalization, some measure can basically be cause of generalization. So that would be subject of future work. Thank you.